Morning. Take-home exams due now, is that right? Okay. How was the rest of it? I haven't seen him yet. Who proctored the exam? Alicia? This is all blur at the moment. Questions? Okay, so the way I see it, where we left off was flow of behavior, is that correct? More or less. We went through the 5 factors that control suspensionality, all that kind of stuff. So we should be around here or here. We've done some of this already, right? Flow of behavior. Why do clay particles, well, let's see how we approach. Most common industrial dispersants are anionic polyelectrolytes, right? So you have, for example, Darvan. There's a bunch of those. There's Darvan C, 811, 821A, number 7. If you need that list, I can give it to you. There's a perception among traditional ceramics that sodium is a dispersant, right? Why do I not like that idea? It's a cation, right? And so it's oppositely charged to the particle surface. So we can do this real quick. You have sodium salts, and you have ammonia salts, and you have PAA, polyphilic acid, and PMAA, polymethylic acid. And this works out to be, for PAA, this is 811, this is 821A, this is number 7, and this is C. There's a perception among people who work in traditional ceramics that you need the sodium salts to be good dispersants for clays, and that's actually doesn't make any difference. PAA is typically a 40% solution. PMAA is a 25% solution. So the other perception is that PAA works better than PMAA for dispersion, and that's not true. It's just that there's more in it when you buy it. The reason there's more in it when you buy it is that these molecules are different chain lengths. This is around 8,000. This is around 15,000. And the consequence of that is that they're a higher viscosity, and so then they correct for that by reducing the amount in water. Perception that sodium is a better dispersant comes out of a problem with the salts that were used to do the experiments. They did sodium and they did calcium salts. They found that sodium salts work better, but it's the anion that's important. Now, most common industrial dispersants such as these, and we have 2 others, by the way. 2 others, we have sodium silicate and sodium hexametaphosphate. And these are inorganic dispersants and really commonly used, and then occasionally you'll see sodium carbonate added in there as a dispersant. And it isn't actually a dispersant. It has to do with this perception that sodium functions as a dispersant, and it doesn't. So what you have is almost all of these are all anionic polyelectrolytes, and there are very few commercially available cationic polyelectrolytes. And the reason is that most of the powders we deal with are compatible with anionic polyelectrolytes, meaning that they would be normally somewhat positively charged, and then you can reverse that charge on the surface, or you can augment it. And most of the things that go into suspension prefer apparently to develop a negative charge. And but for clays, we have 2 charges on the surface. Why 2 charges on the surface of a clay particle? Which ones that they are positive and negative? Why are they different? Why do you have 2 surfaces? Right, so it's a layer structure. So one layer looks like alumina, one layer looks like silica. And so when you have that layer structure, this side looks like alumina, so it would be positively charged. This side looks like silica, so it would be negatively charged. And by bringing in the polyelectrolyte, you only coat the alumina side. So you need actually less dispersant for clays than you would for alumina because you have less surface to coat. And everything else you put in suspension, silica, feldspar, etc., all have negative charges, so it's easier to convert that over to negative charge and disperse the suspension. So the three mechanisms for stability that are projected on the board, you're always trying to overcome van der Waals attraction force between the particles. You can either impart a charge by changing pH, which we do for clays, except that we have some problems. One of those problems is that pH, zeta potential, silica, alumina. So here you're around 8.5, here you're around 2.0. With some neutral pH, you'll have strong negatively charged on silica, strong positive charge on alumina. And if I'm a clay particle, I have oppositely charged surfaces. And then the argument is that one side is negatively charged and one is positively charged. So to get them to be both negatively charged, I have to drive the pH up a long way to be somewhere above 8.5. Okay, that's electrostatic. We get the steric, we can bring in a polymer, coat the surface of the particle to provide a physical barrier to agglomeration. It doesn't work very well. It works pretty well. Aqueous medium. You don't have to go to that sort of trouble in a polar solvent such as water. So almost everybody does electrosteric stabilization, in which you bring in a negatively charged polyelectrolyte. And Darvan and sodium silicate work really well for that application. And so all of this can be predicted from DLVO theory. I'm not really planning to go into that. And I don't really care too much about the pH stabilization part of it. So if you think about it differently, if you're Buffalo, China, and you have a 30,000 pound batch, okay, and you can do the math, 30,000 pounds dry, 20,000 pounds of water, and then you do the math for surface area, so you could assume that that surface area is somewhere in the vicinity between 10 and 15 meters squared per gram. Do your conversion. You've got a lot of surface area. Change pH, you have to add in concentrated acid bases, which has issues for worker safety as well as just the corrosion aspects of all that. Whereas a bucket of Darvan or sodium silicate would work great. That's what everybody does. So you find most polyelectrolytes for industrial applications are anionic polyelectrolytes. You have a problem. That problem is anionic strength. Okay. We can calculate all of that, thickness of the double layer, etc. It's better to illustrate how that works. We went through this chloronitrokaolinite, right? Did all this? The gold particle, Tyson's gold particle experiment brings some gold colloids, demonstrates that the edge of clay particles are negatively charged. Van Olfen tells you that then the surfaces are positive, but that doesn't fit with mineralogy. So we go through all of that. Sodium as a dispersant is folklore. Doesn't work that way. It's the anion that's controlling the behavior. Sodium is just a convenient way to get that into solution. So we have essentially that carboxylic acid group. So your COO minus that comes off of that polymer. You bring in a sodium plus or an ammonia plus, and they will dissociate easily in water, but you could also do an H plus. So that it's actually, this is your charged surface. These ions then associate with that charged surface. You can do it with the acid, with the H. It's not very effective. Sodium's really good. It's dissolved really easily. So we went through this, right? Charge, good of that. All right, so where does that leave us? We can do all of this, determine the surface area, et cetera, et cetera. So We did absorption, surface area ratios. Going through this fast enough for you? So, okay, we do the math. The dispersion of clays works really well based on this ratio of basal plane surface area, okay, and an edge surface area works out almost perfect. We end up at about 58% of the dispersant necessary to coat alumina when you disperse clays. Now, we have a really interesting problem. Let's see if I have it here. So, these are the conclusions. Johnson and Norton in 1941 wrote this article that everybody, to a large extent, misinterpreted. The charge on the Killian particles controls the degree of flocculation. That's all good. But then it says it's governed by the type of cation, and that's where the wheels come off the bus. Okay? Stability of the system is controlled by the anion medium, is governed by the type of anion preferentially absorbed. So they got that part right. This statement here, the type of cation, though, is what confuses people because their experiments are done with either the sodium salt, the sodium silicate, for example, or the calcium salt, calcium silicate, for example. And they found that the sodium salt was much more effective as a dispersant. Why do you think that is? Yeah, because it dissolves, because calcium silicate is insoluble in water. So you put it in water, it doesn't dissociate, you don't end up with that silicate poly anion oligomer, okay? And the consequence of that is you don't get any dispersion behavior by bringing in the calcium salt. You can demonstrate this, by the way. If you take sodium polyphilic acid and put it in water and add calcium chloride, you can precipitate the polyphilic acid because it will reassociate with that calcium ion that will tie up calcium and it will make that polymer insoluble in water. Okay, so we did this. Not sure why it's animated. 13-liter batches. We did kaolin suspensions, of course, on batch by itself. Individual additions of dispersant are blended at the endpoints, which is just an effective way of doing this. You can bring in no dispersant, 0 and 1 milligram per meter squared, and you blend. We aged. What's aging?
Letting it sit there.
Yeah, let it sit there. Typically being stirred or moved. Why do you care? Why do we care? Why did we care? Aging. So, what's going on with aging? You got the first part, let it sit there. Why?
Dissolution of the particle surface.
Okay, so previous literature, you go back a long way, American Ceramic Society, looked at aging of suspensions. What was the conclusion? Why do they age? What a great question. Why do suspensions change over time? You said dissolution. What else? Yeah, so why do they change their behavior? What was thought to be happening? JT, you're biomaterials, aren't you?
I think it's like changing the ion concentration.
Well, that's what we think it is. What did they think it was? Bacteria growth, right? Now these things would sit there and ferment. I have an issue with that, by the way. So, you know the story of China, right? In China, porcelain in China, that you would make clay, not for yourself, not actually for your child, but for your grandchild. Make sense? You make clay, and then it sits there for long periods of time before it gets used. No? You ever heard that? Okay, that's the story. Am I right? Do you know that? Right. So let's think about that from a practical standpoint. If you were a potter, how much clay do you use per year? This is a great question.
Like 200 pounds.
Well, then mostly like a ton, right?
Yeah.
I mean, you use a lot of clay. Like if you're making pottery, say you're making pottery for the emperor in an imperial pottery, you're making a lot of clay, right? And you use a lot of clay every year. So if you're making clay for your grandchild, you've got to say you have a 20-year career, you got to store 20 tons of clay. If you're really productive, you might use 2 tons a day, 2 tons a year, excuse me, okay, which is not unreasonable. If you talk to some of the more productive potters, they use a lot of clay. And so then that clay has to be aged. Okay, that's 20 years, that's 20 tons, and then, but you actually did for your grandchild, so that's another 20 tons. 40 tons of clay you have to store for how long? For 40 years? The math doesn't work out. Right? Plus the way they make clay doesn't match that. They would do all sorts of interesting things, and I've heard of potters adding things to clay, right? You know, you're up, you're down, you're out, you're in. Oh yeah, you're in. And then beer, those sorts of things to help bacteria growth. Have you heard that? People do that?
Yeah.
Yes. What do you get? You can get bacteria growth, maybe. You also get stinky clay, okay, which might be the same thing. But the issue is you use water out of the tap, right? And there's things in the tap water to prevent bacteria growth that probably gets in the way, but it's not necessary. So this aging and bacteria growth in clay, there's an interesting article from like 1920 where they did the experiment and they did the whole petri dish thing and counted clay or bacteria colonies or whatever it was. Right? Can you grow bacteria in clay? Absolutely. Why did we do it? Because we didn't want to talk about aging. Okay, so if you made the suspension, you test them right away. And somebody in the audience is going to argue with you that you didn't age the clay and the results will be different. So we aged the clay. Now they can argue we should age it longer or differently. It doesn't make a difference. We aged the clay. And we didn't test anything for 2 weeks. Good. Does the clay change with time? Plasticity change with time? Yes. And why? Don't stop now, you're on a roll.
Change in ionic strength.
Yeah, we think that the clays slowly dissolve a little bit with time. That takes time. We have a bunch of data that shows how long that takes. Okay? And typically that dissolution process is doesn't take very long, but we think part of it is associated with mixing. So if the clay is not mixed well, okay, then it takes a while for water to get around all the particles. As it sits there, that process happens. And as that occurs, then any dissolution that's going to happen gets delayed until that process is more or less complete, right? So there is a benefit of letting it sit around just for homogeneity purposes, okay? But the times that are required are not particularly long. So you will find this, that in really well-run factories, okay, Corona's factories in South America, some of the best run in the world. I've had 4 master's students from there. They're really brilliant, typically. They run that process, and clay, by standard operating procedure, sits for 2 weeks before it goes in to be formed. And if they don't have enough clay available, they stop the process until it's aged that period of time. What does that do for you? Well, you could argue that it becomes inefficient, right? That they've had that clay sitting around and they could probably go back into production earlier, but what they find is that their yields in the factory are better if they let that clay sit for a period of time. And that actually makes sense in the long run if you think about it. All their machines, forming machines, are set up based on a certain rheological behavior. If that clay does not come in with that same rheological behavior, then your forming processes don't run the same. Then your losses increase, basically. So by waiting to run that clay in the process, they get better consistency. Now you can say, well, they're putting fewer pieces in the box. Yes, but they're also recycling fewer pieces, so it works out better for them. So well-run factories will let that clay sit for that period of time and then incorporate it into the process. And you will find, though, that people get impatient. And if their clay hasn't aged long enough, they go, oh, it's okay, we're going to run it through the process anyway, and then their yields are affected. Okay? So we argue that aging is due to interaction of the particles with water and dissolution of soluble species, and then that changes ionic strength. Okay? Ionic strength plays a big role in plasticity. Porcelain batch, we talked about this, 95% of the surface area comes from the clays. We have actually we had 5 dispersants: sodium polyphilic acid, polymethylic acid, sodium hexametaphosphate, which is calgon, sodium silicate. This X value here we measured by chemical analysis, and the pH at which sodium silicate is produced dictates the ratio of sodium to silica, and therefore the polymerization of the silicate ion. And there's a really nice book by a guy named Eiler on that subject if you're interested in the chemistry of silica. And then we did soda ash, not acid dispersant, but what you see here, these are all sodium compounds, right? And so the idea was to evaluate sodium, and then we have a blend of sodium silicate and soda ash, which is really commonly used, okay? Whereas typically 1:1. And interestingly enough, we think it does a different purpose than actually improving dispersion. Okay, so these are the dispersion curves. What do you see? X-axis is then amount of dispersion corrected for surface area. This is for a 49% porcelain batch. So that means it is this batch back here, excuse me, this one, okay, kaolin, ball clay, methane, cyanide, quartz, alumina. This batch at that time was actually Buffalo China's composition. Okay, so one small variation, they didn't use EPK, they used tau kaolin #6. We used EPK because it was convenient. And then eventually they went to a 325 mesh quartz here. A400 was common, A10. I learned this recently. A10 was really high volume aluminum made by Alcoa and then Almatis that was used in the spark plug industry. And they don't use it so much anymore. So it's harder to get. Anyway, this batch composition was interesting for a couple of reasons. We had been working with the whiteware manufacturers, the Whiteware Research Center, and everybody was under the impression that their batch was a secret. I told you this before, right? Okay. As one friend of mine said, that he thought he should keep his batches, clays compositions, a secret to protect the rest of the industry. He didn't think anybody should have to deal with all the problems he had to deal with. That's what he did. This actually represented a deviation where Buffalo China said, we agree with you, and basically, because our batch composition knocked us so out. So we actually used, instead of making up a composition, we used one from industry. But the fact that we really do that was a deviation. All right, so what do you see?
The low point and viscosity.
Okay, so let's talk about how about the 4 dispersants? Darban 7, Darban 811, sodium silicate, sodium hexametaphosphate. And actually for the low-hanging fruit here, what's the?
Well, all except the blue triangles are the same.
Yeah, so there's no difference in the dispersants, right? So we're not adding Darban 811, we're actually correcting for the amount of polyphilic acid in Darban 811. So then if you have to bring in more Darban 7 than Darban 811 because they're different concentrations of solids within that solution, but we did all of that. So now we're comparing everything on an equivalent basis. And you find that the dispersants all behave exactly the same, with the exception of the triangles at the top, sodium carbonate. Sodium carbonate doesn't work very well. So this point was to illustrate that sodium is not a dispersant, as the point of this was, right? They would have to all behave the same if sodium was a dispersant. They don't. So you do see a drop in viscosity for sodium carbonate, but it's only about a factor of 10, right? Where the others are dropping 1, 2, 3, or the magnitude, a little more than that actually, to get to the minimum. So sodium carbonate doesn't work that well as a dispersant because it's not a dispersant. Why do you think the viscosity drop with sodium carbonate? We'll come back to that in a minute. Okay. If I blend sodium carbonate and soda ash, I get this curve. Sodium silicate is dispersing the system effectively, And then sodium carbonate is not doing very much, so it's dominated by the sodium carbonate initially. Before I get to surface coverage, if I get to surface coverage, then it matches the curve for sodium silicate. So what you can see is that, and you could argue that these are additive effects, okay? You also see then the shift of pH in the system. What we see is that the shift of pH for soda ash drives up the pH, and that may help me, in fact, to get up to pH of 10. So my small improvement in dispersion is really because I boosted the pH a little bit. It's also possible that I've helped by tying up calcium or something else in solution, which I'll talk about in a minute. So, milligrams per meter squared, log viscosity, okay. I get my curve looks like this. There's my minimum, close enough, okay. Two things. It doesn't come up quite as much, okay. This increase in viscosity here, okay, is due to sodium ion concentration. So when I bring in a polyelectrolyte like sodium silicate, I am also increasing the concentration of sodium ions in solution. They are oppositely charged to that particle surface. Therefore, my viscosity goes up. The minimum here, which is about 0.15 or 0.17 or so, is about half the dispersion level necessary to disperse aluminum. Now, if I'm doing this with clay, it's a porcelain body, what's the problem if I disperse at the minimum? So, what's the problem if I disperse at the minimum?
If it decreases the concentration at all, it will have a large effect on viscosity.
Well, yeah, it will have a large effect on viscosity. No change in concentration to speak of, though, right? Because I'm adding only a small, very small amount of water that comes in with my dispersant, so I'm not really changing concentration. Why don't I want to disperse at the minimum?
Don't get full coverage. So it increases.
So I don't want to disperse at the minimum. Not if I do, I get full coverage. Why don't I want to disperse at the minimum? Okay, so if you back up a bit, look at the composition of batch, right? What do I have? I have, this case, 36% clay, and the balance is nepheline cyanide, quartz, and alumina, right? If you look at the surface area differences, you can see that these particles, nepheline cyanide, quartz, and alumina, or feldspar and quartz, or whatever, are huge by comparison, right? They are 50 microns, 35 microns, typically, okay? And there's a broad particle size distribution. But then, how big are my clay particles? Well, they're on the order of about a micron, right? So I get this three-dimensional network of clay particles that are suspending these much larger particles. And if I perfectly disperse that network, those large particles then settle out. And I segregate my batch by size. So the quartz and the feldspar particles will settle. And when they do that, okay, I don't have the same batch composition anymore. If you recall, we did this clay characterization. Okay, and we dispersed the system. Okay, we disperse the system, and you can see when it's dispersed. Okay, this is all the quartz sedimented out. And so we did this intentionally here to separate by size. But if I go to a normal batch, I do the same thing. This is just the clay, right? So the feldspar particles that were in the clay to start with, quartz particles that were in the clay to start with, when I disperse it, they segregate by size. If I take the whole batch and I do a great job of dispersing, okay, then the quartz and feldspar particles settle out. So we don't like to disperse to the minimum. We disperse typically to somewhere around here. This is our window, if you will. So I can drop the viscosity down significantly, and therefore I can increase my solids loading, I can control the suspension well. But, okay, what I get out of that is my particles stay dispersed, they stay suspended in the system, okay? And so I don't end up segregating by size. Okay, now, that brings up a small other problem for us, and that problem is that the industry has adopted terms, and one of them is stable versus unstable, and so then the problem is in a clay suspension the term stable doesn't mean that it's dispersed to the minimum, but it's dispersed to the point where the particles do not segregate by size. Whereas if you're in the advanced ceramics industry, the term stable would mean dispersed to the minimum. So we have a terminology problem, so we prefer not to use stable and unstable. All right, so we don't typically change the pH. We monitor the pH, but we do not change it. And so what you see is that pH will drift. Our minimum is someplace around here. So our minimum, if you will, I end up with sodium hexametaphosphate and sodium and polyphilic acid, methacrylic acid. Almost no change in pH. We start somewhere around 7.5. Small change in pH here. If I over-disperse the system, my pH goes up. But we're really in a pretty narrow range from about 7.5 to about 8.5, where we're at our minimum in dispersion, but we really don't want to be at that minimum to begin with. So we've partially dispersed the system. So, these are 1-to-1 sheet silicates. What happens when we go to 2-to-1? So we did a bunch of studies for commercial clays. V-gum T is a manufactured product. It is it's a smectite with magnesium. The values here are, and then Van Gel is something similar, Wyoming bentonite, bentonite L. These are two ball clays that came out of Indiana, and this is out of Mississippi. These are their surface areas. So notice that bentonite L is 95 meters squared per gram. Wyoming bentonite is only 31, so almost 32 meters squared per gram. V-gum is 90 meters squared per gram. Those values are measured on the clay when it's dry. Does this make sense? Okay. And when you put them in water, they will delaminate depending on the nature of the clay. Bentonite L is for light, because the bentonites tended to have some iron in them, and that made them discolored. And so they developed this product, bentonite L. It actually doesn't work that well. It doesn't work nearly as well as bentonite. It has to do with its ability to dissociate. So what you see on the right-hand side is that the volume concentration necessary to get to a certain viscosity value. Does this make sense? In other words, I'm going to put this clay in water, targeting 100 pascal seconds as viscosity. How much clay do I have to put in water to get to that dispersion, or to get to that viscosity value? So what you see is that V-gum T requires 3 volume percent. Okay? So 3 volume percent, when I showed you those clay sedimentation columns, those are at 3 volume percent. Okay? So V-gum T at 3 volume percent gives me 100 pascal seconds. Van Gel needs 4.5, Wyoming bentonite requires 4.5. But bentonite L requires 25 volume percent, even though it has a surface area of 95 meters per gram. So these are, by and large, the first top 4 here are 2-to-1 sheet silicates. Okay, they are typically montmorillonites. So they have this structure instead, with an oriented water layer. Okay, and then this dissociates in water. Now, if I look at this structure compared to kaolinite, I mean, obviously 1-to-1 versus 2-to-1. This basal plane and this basal plane should be identical, yes, in silica, whereas these are different. So I would expect the 2-to-1 sheet silicate to behave differently in water than a 1-to-1 sheet silicate. Okay, and you could argue that the edge of this structure over here, right, could be positive and negatively charged, probably more negatively charged because of the silicate. Okay, so then the question would be, how do dispersants work? We're still sort of, shall we say, struggling with this problem. Let's go here, there's muscovite, mica, etc. I'm going to skip all that. This idea of dissociation, okay? If I put sodium in between the layers, and I stick them in water, the sodium will come out. It's an exchangeable cation. Sodium comes out, and then when the sodium exits that structure, now you end up with two sheets of negative charge, and they will automatically repel each other in water, and that clay will dissociate. Keith Simpson over in Art Design discovered that if he took bentonite L, and it's supposed to be a calcium bentonite, and he added a lot of sodium to the system, he could get it to behave more like bentonite itself. Okay. So these things delaminate. So the question is, if I brought in small amounts of 2-to-1 sheet silicate into a clay structure, how does that affect my viscosity? Does this make sense? Okay. So what we're trying to do is figure out how things work in terms of dispersion levels. I have swellable and non-swellable 2-to-1 sheet silicates. Let's see if I have a picture of that. Yes, here. Zip right in my eye. Okay. So, if I have sodium in this layer, then it's considered to be swellable. That means that the clay will delaminate or expand by exchanging those sodium ions in the structure. If I have calcium in between the layers, though, the motivation to take the calcium out and exchange it with something else is pretty low. So therefore, that clay doesn't expand. Bentonite L has calcium in between the layers, whereas Wyoming bentonite has sodium in between the layers, and so sodium bentonite will delaminate in water, and the bentonite L doesn't tend to do that as well. Okay. So we did different additive levels to see what happened to viscosity. Here is V gum T. As a function of dispersion level, sodium hexametaphosphate and sodium polyacrylic acid. And everything was normalized. The surface of the viscosities are normalized to 1. And so when you add in dispersant level, solid sodium about 3 volume percent, change your dispersants, you see that you can marginally decrease the viscosity of V gum T at 90 meters squared per gram. Part of the argument here would be that my 90 meters squared per gram isn't a realistic value. Put it into water, delaminates, my surface area goes up. You calculate that it is, but you can't measure it very well. If I do montmorillonite and bentonite, Van B, Wyoming bentonite, what do you see? This is just for polyacrylic acid. We didn't do the sodium hexametaphosphate. Not much effect on viscosity in general. So these adding dispersants into the system doesn't appear to change the viscosity very much. Okay. So then we said, well, what if we added small amounts of these materials to existing suspensions? Here I have an odd case, 25 volume percent. I bring in sodium hexametaphosphate or sodium polyacrylic acid, and with dispersion level, my viscosity goes up. The kaolinite illite mixtures, these are the 3 other commercial clays. They basically disperse pretty well. Indiana ball clays, sodium hexametaphosphate behaved reasonably well, not too good. And then if I add montmorillonites into the clays, these are 2 magnesium montmorillonite and calcium. I add the amount of perspectite added to the suspension. Look at the change in viscosity, not much difference. You follow what we're doing here? Can someone give me a synopsis of what we're doing? Can you do it? What is it that we're trying to show? We're taking clay suspensions basically, and we're adding small amounts of smectite to see how it might affect the viscosity. What's the motivation? We're getting clay out of the ground. I have my big impurity is what?
Silicon.
Quartz. Okay. Then I have minor impurities, which are smectites typically. 2-to-1 sheet silicates that show up in the whole clay deposit. All right. When I add my dispersant in, sometimes it's more effective or less effective. I'd like to know how much of that smectite I have. The other thing that's happening in the process of the clays is they are blending clays with different piles in the mine to try to maintain that cation exchange capacity. Okay. And then my question is, how sensitive is the viscosity of my system to small changes in 2-to-1 sheet silicates in the system? So here, if I'm adding in a calcium octylonate or magnesium, I get no change in viscosity. And this is the added smectite and total amounts of suspension surface area. The top is my solids loading, so I'm adding 0.25% by volume, and I get no change in viscosity. If I go to a swelling clay, such as a sodium, this is a Wyoming bentonite now, and I have 2 cases here, 30 volume percent and 20 volume percent. If I add, if I look at it this way, if I add roughly 3% of my surface area is added to my suspension, I increase my viscosity by a factor of 10. Okay? And if I'm in the 30 volume percent case, I add roughly 2% and my viscosity increases. So I see a number of things here. One of those things is that the solids loading has a big role as well. I add small amounts of a 2-to-1 sheet silicate and my viscosity goes up. Okay. Now we use that sometimes in suspensions and in clay bodies. If I get a clay body that's not particularly plastic or difficult to form, we might add in 1% or 2% bentonite or smectite. Okay? You should resist the urge to add in more than that. Most you're going to add is about 2% by volume, or by mass actually. And that small addition level makes a big difference in plasticity. The other thing it does is it helps keep things suspended, gives you better forming behavior. Okay. So the 2-to-1 sheet silicates, they are typically, go back to the previous slides, insensitive to the addition of dispersant, but they also drive up viscosity depending on which one you select. Okay. Ignore the zeta potential measurements. And I'm going to go to ionic strength. Okay, so we're dealing with all of these clays. What's the charge on the particle surface? For just about everything. Negative. Okay? So charge on particle surface is negative. That means when I put it into suspension, cations are important to me. These are counter ions. So that means that they are oppositely charged to particle surface. We have a double layer model that we just blew through basically, but if I increase the concentration of ions, then I will compress the double layer, right? I'll make that thickness of that double layer smaller. It doesn't make a difference how I got charged on the particle surface. I can do it through reaction with an acid or base, okay? So electrostatic stabilization, or I can bring in a polyelectrolyte, okay? So Darvan, for example, or sodium silicate, and I can create that negative charge on the particle surface. Doesn't make any difference how I get there, okay? Cations then are oppositely charged. They help to compensate for that charge simply by being in solution, and I end up compressing the double layer. So we did this, 6 salts. The salts were not selected randomly, okay? Because I have sodium chloride and sodium sulfate. Why? Because folklore tells me that sodium is a dispersant, okay? And then I have calcium chloride and calcium sulfate, and I have magnesium chloride, magnesium sulfate. And the reason is because I have 2 things that I'm fighting at the moment, okay? One, I have sodium as a dispersant. Which I believe is wrong. I have another problem, okay? This comes out of an industry test to determine then soluble sulfate. Soluble sulfate means I have a concentration of SO4 2 minus in solution. And the belief is, the problem is that you can demonstrate it with data, but it is false positive, if you will, that the concentration of sulfate then, viscosity, say viscosity is a function of soluble sulfate levels. The reason that that is the case is because they would bring in sulfate as calcium sulfate. This is actually gypsum. Okay, they would bring in calcium sulfate as gypsum to change the sulfate level, and then they monitored the viscosity of that system and demonstrated that as you increase the sulfate ion concentration, viscosity increases. To figure out how much sulfate they had in solution, they would bring in barium, and then barium ties up the sulfate, takes it out of solution. You can measure then the amount of barium sulfate that you're precipitating and get a sulfate ion level. The other thing that happens though is that the carbonate that comes into the barium carbonate will precipitate out or tie up calcium. So it takes calcium out of the system. So you actually clean the ionic strength of that system by the addition of barium carbonate. Okay. Leads you to the erroneous conclusion that sulfate plays some role in the viscosity of that suspension. Does that make sense? You understand? I get to that erroneous conclusion. We would argue colloidal theory dictates that it has to be the cation, all right? But the problem is that when you do the test, you can lead yourself to believe that it is the anion. All right? Why do I say the anion doesn't make any difference? Have a negatively charged particle surface. Therefore, the anion doesn't actually help in that compression of the upper layer. Okay, it's really going to be the counter ion that's going to do that. So, anion is a co-ion. So, this experiment is set up to do 2 things for me. Let me evaluate sulfate, so I get sulfate from magnesium, calcium, and sodium, and then to also demonstrate that sodium is not a dispersant. Okay, so that's the way that it was done. What would you expect to have happen? Oh, magnesium and calcium should behave similarly, okay, and it shouldn't care whether I have the sulfate or the chloride, right? And sodium will not behave as a dispersant in the system. If I increase the sodium ion concentration, my viscosity will go up. So the thing here, though, there's an assumption, and the assumption is that these ions all behave as indifferent electrolytes. Okay? What does that mean? What is an indifferent electrolyte? What's an indifferent electrolyte? So if it's an indifferent electrolyte, it means that the anion and the cation have a similar affinity for the particle surface. So you don't get specific affinity of one ion over another. Okay? So let's assume that we have an indifferent electrolyte. Next statement here, the green one, says salts were always added as a saturated solution. Okay? First year I was here, taught this class, isn't offered anymore. 414, I think it was called. And we did the ion exchange experiment, and we added salt into the suspensions, and nothing happened. Because that salt crystal would go into water, and then the particles would agglomerate around the salt crystal. They would float around as this blob for a period of time. It took like 2 weeks for that salt crystal to slowly dissolve into the water. So, we don't do that anymore. We don't like to add undissolved salt into these suspensions. They don't work well. It's very easy to create a saturated solution, so we have saturated solutions in the lab. And we use those saturated solutions to bring salts into water. How do you create a saturated solution?
You just put salt into the water until more salt in.
Exactly. Put salt in water and let it sit. Doesn't take very long. If you have salt still at the bottom, you have a saturated solution. Okay. What's the salt? What's the salt? define a salt for me. Anything that dissolves in water. Fair enough? So I argue that you would want to say that sodium chloride is salt. That's unfortunate. It's table salt. Okay? There's a whole book on this if you're interested. It's actually pretty good. Okay? But sodium sulfate is a salt, calcium sulfate is a salt, okay, magnesium sulfate is salts. They're all salts. They all dissolve. So here's what we get. Pure viscosity on the y-axis, cation concentration on the x-axis, 30 volume percent suspensions, and the way that these were done was that we added, or made up a stock suspension, and then added a saturated salt solution or a diluted salt solution to increase the water content or drop the solid volume to 30 volume percent. Okay, so the amount of water that you add to that 30 volume percent suspension, the amount of salt you can dissolve into that water dictates your maximum possible ionic strength in the system. Okay, so that, and the other thing is, you don't take that container saturated salt solution, you don't shake it up and use it, because then it takes the undissolved salt particles and puts them up in suspension, and then you don't know what you're adding. You allow it to settle, you just decant off the clear liquid on top, that's what's added. All the experiments are done the same way. The other thing it does, it gets around problems with hygroscopic materials. So, for example, if you have, say, calcium chloride, which is commonly used as ice melt, right, and let it sit out, in the summertime it gets humid, picks up moisture, all the particles stick together, okay? Now what happens is that amount of water it picks up is not insignificant. And so if I'm weighing that salt out and get the amount of salt, I will get less salt than I should have because of the water that picked up from humidity. Saturated solution gives me the same amount every time. So I'm adding it as this whole solution. Viscosity below a certain point, unaffected. These three levels have to do with dispersant level. This is no dispersant added, 0.02 and 0.05 milligrams per meter squared. Okay, and you get to a certain point, and then you see a rapid increase in viscosity, and above that point, viscosity plateaus again. Okay, that point where the viscosity increases rapidly is called the critical coagulation concentration. And there are two ways that you get to that. Critical coagulation concentration, there are two ways to get to that. And in these experiments, we have what's called a fast coagulation event. Okay? The other is what's called a slow coagulation event. So if you work in a very dilute suspension, you can change your salt concentration, and then you establish a time frame. It could be half an hour, an hour. It doesn't make any difference. You select that time frame, then you come back and you evaluate your suspension. If you have exceeded the CCC, you will hit what's called a cloud point. And that dilute suspension will start to look like clouds, not like today's clouds, which are indistinct, but where it will start to have that billowy cloud texture. And you can see that in the suspension. It's called the cloud point. So what you have is particles have Brownian motion, and they're moving around, and they get close to each other and they stick together. And if they are, if the attraction potential is great enough, they don't de-agglomerate, and those flocks will grow and they'll form that structure. Okay. It takes time because you have to rely on Brownian motion for particles to move around and to find each other and stick. And if you're below the critical coagulation concentration, they will stick and then spontaneously de-agglomerate, and so you can then define that. In a fast coagulation event, there is no Brownian motion contribution to speak of because your diffusion distances between particles is extremely small. So what we get is an instantaneous change in viscosity with the addition of salt. That would be a fast coagulation event. Now the way that we prefer to do this is to take the derivative of this curve, okay, to determine the greatest slope to tell us that we're at the critical coagulation concentration. You work out to be in the middle between 1 and 10. So So you're about, say, 3 millimolar, something along those lines, for, in this case, calcium. So this is cation concentration. So 1 mole of calcium chloride brings in 1 mole of calcium and 2 moles of chlorine. Okay? If I do sodium sulfate, I get something similar. The peaks are not quite as high. I'm not exactly sure why. Nonetheless, same sort of thing. I add cation concentration now corrected for sodium 2+, okay, and you can see that they also increase the viscosity of the system. Okay. Now, if I do calcium chloride and calcium sulfate, what do you see? I would say that the two curves are indistinguishable. Okay, but I would also see that apparently for calcium sulfate, we didn't finish the curve. So your first assumption may be that my graduate student was lazy, and that may not be a bad assumption, but it's not correct in this case. I have another case where I think it is. Okay, but why is it that I don't have? Why didn't I finish the curve? Why didn't she finish the curve with calcium sulfate? Say again.
Saturation.
Yeah, so calcium sulfate, gypsum has a low solubility in water. Gypsum is commonly used to change the viscosity of suspensions, but the concentration of sodium or calcium that you get out of that is small. But you look at this, there is no difference between calcium sulfate and calcium chloride for its effect on the viscosity of the system. So you would conclude that calcium is responsible. And then to demonstrate that, why not compare calcium and magnesium, which we do here, and you can see now that calcium chloride and magnesium chloride have the same critical coagulation concentration, which is here, okay? And sodium actually requires more. Now here I would argue that these points down at the bottom is because of dedication to craft, right? But this factor of 8 difference between sodium and magnesium and calcium is predicted. Make sense? Okay. Divalent cation is much more effective at coagulating the system than monovalent. All right. And so you can do it with sodium, but we prefer to do it with calcium and magnesium. All right. Then I had a student look at what happens if I blend these. So I blend calcium and magnesium and sodium together. We're really looking to see if the results are additive, meaning that the concentration of calcium plus the concentration of magnesium plus the concentration of sodium corrected appropriately for charge on the particle surface. So your ionic strength contribution, actually thickness of the double layer, 1/L scales, or you should say as a function of the square root of C sub I, Z sub I squared, okay? And it is the summation of these. So it's the concentration of species I times the charge squared plus the concentration of species J times the charge on J squared. So what you get out of this is that whether the charge is positive or negative is unimportant, but you will also see that your 1/double layer thickness, so this is inverse, okay, scales linearly with charge with the square root of concentration. So that means that if you want to see the same effect, you have to add a lot more of, say, a smaller valent, a lower valent cation, and you sum all of them together, and that will let you calculate the thickness of the double layer. So the question is it truly additive? And the student did the work. Pete Kopinski was his name. And divalent cation concentration. These are the blended salts. Okay. The red line and the blue line are tracing just magnesium and calcium. But basically, you see that the points populate. There's no apparent contribution of one salt over another. And he did a matrix where he blended sodium, calcium, and magnesium, and looked at the ratios, and then the change in viscosity. This curve mimics the other. Let's talk about sodium for a minute. This is the most dangerous slide in my collection. I have a lot of slides in my collection. Okay, so the way that we did this experiment, let's go back a couple steps here. Let's go to here, for example. So the concentration of sodium ions, all right, is ignoring then the concentration of sodium that comes in with my dispersant. So we initially assumed that that concentration of sodium coming into the dispersant was negative. Does that make sense? Okay, so I'm bringing in sodium polyacrylic acid in this case as a dispersant. Instead of the slide, that's what it is. All right, so I'm adding sodium into the system. But I'm ignoring that sodium when I bring in my salt. So I say, well, I start off, I put 0.1 millimolar in here of sodium, okay? But I ignored that there was any sodium coming in from the dispersant. And then I put in, I don't know, you get up to 1 millimolar and 10 millimolar and 100, etc. Okay, so when we get here, what happens is that this is my curve. This is for sodium chloride. This is the sodium addition. But this curve is the amount of sodium that comes in. This is a change in viscosity, the sodium ion concentration. That's why this is a dangerous plot. Okay. So I start with my suspension, and I add in sodium polyacrylic acid. And I bring it in, and this is the concentration of sodium ions that's brought in with that level of dispersant at that point. Then I add in more dispersant, my sodium ion concentration goes up, my viscosity drops, and I get to a minimum here at the minimum in the dispersion curve, okay? And that's my starting sodium ion concentration. So in fact, this point added to this point is my total sodium ion concentration in the system. So the amount of sodium that's brought in with the dispersant is not insignificant. Make sense? So when you do that, you add this plus this. Oh, that's the square one. You can see it overlaps that the circle, but it's offset a little bit. And then this now added to that amount, not to this amount, to that amount, because this is my baseline, is the amount of sodium that comes in with the dispersant at the minimum. Then I'm going to add the amount of sodium here at 10 millimolar is added. So my point here, if it goes from 80 to 90, that's my 10 millimolar. So it looks like it's a very small contribution. My viscosity goes up, and you see eventually they match up at the top. Okay, so up here, this is then corrected for the sodium ion level. What does it do for me? It makes a small change in the critical coagulation concentration in the system. Okay, but it's small. However, if I look at the circles here, you see that the circles go up, and after my minimum viscosity goes up. And so the rise of viscosity that's associated with excess dispersant is due to increase in sodium ion concentration. And we see something really interesting here that we rarely talk about. Notice that my viscosity plateau that would be obtained by adding excess dispersant is lower than my viscosity plateau associated with adding excess salt. Why? So what you have is this. Milligrams per meter squared, log viscosity. My curve comes down like that, right? And this increase in viscosity is due to the concentration of sodium ions. Okay? And then do this, exactly this plot here, concentration of sodium, log viscosity. Okay? My curve comes down like this. And my other curve comes down like this. So this is concentration of sodium salt. This is from excess dispersant. My question is, why? Why the difference in the peak viscosity then? Does that make sense? And the answer is, it's interesting. We think this is called depletion stabilization. What that means is that when I bring in excess polymer into this system, excess dispersant, where does it go? Where's excess dispersant go in the system?
Yeah, the suspension for the nitrate.
Say again?
Just the suspension.
It just stays in solution. All right. So that polymer now is in there in solution. And what it does is it gets in the way of other particles agglomerating. They're agglomerated, but it's also providing some room in that suspension for them to move around. It's basically getting in the way of them agglomerating in the way that you might predict them to agglomerate in the absence of that polymer. So that's called a completion stabilization mechanism. In other words, you can get a reduction in viscosity by simply having other polymers in the system. So this plot here shows us a lot. But one is that the sodium ion concentration that comes in with the dispersant is not insignificant. Okay? And then lastly, we can calculate that double layer thickness, and what you see is that this is for what are called symmetrical electrolytes. So sodium chloride is a symmetrical electrolyte. Magnesium sulfate is a symmetrical electrolyte. But calcium chloride is not. Okay? So this is called the Debye-Huckel approximation. And what you see actually is that magnesium sulfate is not an indifferent electrolyte compared to sodium chloride and calcium sulfate. It becomes more obvious when we do what are called numerical calculations. So here, 5 of my 6 salts behave exactly the same, and magnesium sulfate behaves differently. So, how does magnesium sulfate behave? Is it more effective as a coagulant or less effective? So what you have is your double layer thickness is on the x-axis here, on log scale, apparent viscosity on the x. What you see is that you apparently are coagulating at a larger double layer thickness with magnesium sulfate. That suggests that magnesium sulfate, the magnesium ion, has a greater affinity for the surface of the particle in the presence of sulfate. I don't think that that's predictable if you have to measure. But effectively, 5 of our 6 salts behave as indifferent electrolytes. It means they have similar affinities for the particle surface. So, I propose a revision to Johnson-Norton, but we don't have to deal with that. Okay. So this is where we're at. Kaolinite particles have opposite charged surfaces based on structure. Okay. Anion species, polyanionic species are responsible for dispersion. The cations, sodium or calcium or magnesium, cause coagulation. And we're not going to deal with the zeta potential issues. Okay. And then what I have is we got a whole bunch of slides on aging that we will address shortly on Wednesday. Okay. And that will get us how to put a behavior into forming processes. Okay. So what I need from you, roll me your take-home exams. Okay. Today would be great. And then I'll get your other exams back and we shall agree those. And I owe you a makeup class or 2. 1, right? Only 1 makeup class? Because I had class on this before I left. And then I had, you had the exam. So I'm behind 1 class. Questions? You have a homework assignment, right, for this? Okay. Good? Do Wednesday for take home?
Yeah, I also.
I don't care.
Okay.
Fine, Wednesday.